Now, just like we built up our limit laws from sort of basic functions, we're going to build up continuous functions from our sort of some basic functions. First of all, if we have two functions f and g that are continuous on an interval I, then their sum, difference, and product are also continuous on this interval I, and also if I multiply f by a constant k, it will also be continuous on that interval I. The ratio of f and g will be continuous on the interval I, except where g of x is equal to 0. I can't divide by 0. That leads to a discontinuity. Okay, now using our limit laws and these facts right here, we can actually build quite a few continuous functions. First of all, polynomials. You can show that monomials and constant functions are continuous, and then using these facts here, you can show that polynomials, which are sums of monomials times constants, are going to be continuous on the interval from negative infinity to infinity, i.e. they're continuous everywhere. Rational functions f of x, which are ratios of polynomials p and q, are going to be continuous everywhere except for where q of x is equal to 0. So basically they're continuous on their domains, wherever they are defined, and that just follows from the fact that polynomials are continuous everywhere and the ratios of functions are continuous wherever the denominator is non-zero. Okay, so what about some of our other functions? Well, how about trigonometric functions? Sine and cosine are going to be continuous on the entire real number line. The reason here is if we think of cosine and sine as the coordinates of a point on the unit circle with angle x to the positive x-axis, then as we continuously vary this angle, the point on the unit circle itself is continuously varied. So the x-coordinate and the y-coordinate of this point continuously vary as I vary this angle. Then using our other rules, for example for quotients, we can get the domains, we can get the places where tangent, secant, cosecant, and cotangent are continuous. Tangent and secant will be continuous on their domains, being ratios of two continuous functions. So that means continuous everywhere except for plus or minus pi over 2, plus or minus 3 pi over 2, plus or minus 5 pi over 2, etc. And cotangent and cosecant will be continuous wherever they're defined, which will be when when sine is non-zero, so when x is not equal to 0, plus or minus 2 pi, etc. What other functions do we have? Well, we have exponential functions. Now, e to the x is really more or less continuous on the entire real number line by definition. That is, to define e to the x for a real number x, you generally have to define it as the limit of e to the x over rational values of x. So just by definition it's continuous, but here's the graph and it looks like it's continuous too. Okay, what else do we have? Inverse functions. Inverse functions are going to be continuous on their domains. Why? Well, so long as they're the inverse of a continuous function. Why? If I start with a continuous function, I get the graph of the inverse function by flipping it around the line x is equal to y, as you see right here. Well, if I start with a graph that I can draw without picking up my pencil, I end with a graph that I can draw without picking up my pencil. So I'm left with something continuous. So in particular, we have that the natural log is continuous for 0 to infinity, excluding 0. And we have that arctangent is continuous on the entire real number line. So now we can figure out where functions that are built up out of all of our basic functions and the arithmetic operations are continuous. So for example, where is log of x over x minus 1 continuous? Well, I have a ratio of functions, and I know that it's going to be continuous wherever both of them are continuous, but also where the bottom guy is not equal to 0. So, log of x is continuous on the interval from 0 to infinity, excluding 0, because that's a fact we just said. X minus 1 is a polynomial, so it is continuous everywhere. Where is the overlap? Between 0 and infinity, because this is continuous there, log of x is only continuous there. I also have to exclude there where the denominator is equal to 0, which is when x minus 1 is equal to 0, or which is when x is equal to 1. So if I take the interval from 0 to infinity and take away this one value, I'm left with a union of two intervals, from 0 to 1 and from 1 to infinity. So your question for this video is, Where is the function g of x equal to the square root of x over e to the x minus 1 continuous? Do the same basic thing. Figure out where each of the constituent functions is continuous, and then see if there are any other problem values when we divide these two guys. One nice thing about continuous functions is they play well with limits in this following sense. Suppose f of x is continuous. Then if I look at the limit of f of g of x, I can actually bring f outside the limit and then just evaluate the limit of g of x and plug that into f. So the limit as x approaches c of f of g of x is f of the limit as x approaches c of g of x. For example, let's evaluate the limit as x approaches 1 of log of x minus 1 over x squared minus 1. The problem here is if I were just plugging 1, I would get 0 over 0 on the inside. I can't do that. Now, since log is continuous wherever it's defined, I can actually bring the log outside of the limit, as I do here, and just evaluate the limit as x goes to 1 of x minus 1 over x squared minus 1. Since I have a rational function, where when I plug in the value 1, I get 0 over 0, that means that I probably have some factors that are going to cancel. So I factor the top and the bottom. The top is still x minus 1. The bottom becomes x minus 1 times x plus 1. Well, there's my common factor, x minus 1. I cancel those two guys out, and I'm just left with, on the inside, the limit as x approaches 1 of 1 over x plus 1. Now, the fact that a rational function is continuous wherever it's defined means that I can just plug 1 into this expression. And I get, contrary to what I have written here, the natural log of 1/2. Great. Now, a corollary of the previous fact is the following. If g of x is continuous at c and f of x is continuous at g of c, then f of g of x is continuous at c. The upshot here is that the composition of two continuous functions is continuous wherever it's defined. Let's do an example. Where is h of x, which is log of 1 minus cosine of x, continuous? Well, the inside is always defined. The only problem is when log is undefined. Now, log is defined for x greater than 0, so h of x is defined when the inside is greater than 0, i.e. when cosine of x is less than 1. Well, when do things go wrong? When cosine is greater than or equal to 1. And that only happens when cosine is equal to 1, i.e. when x is equal to 0, plus or minus 2 pi, plus or minus 4 pi, etc. Therefore, h of x is continuous between any of these two values, which we can write as follows. The open interval from 2n pi to 2 times n plus 1 pi, where n is any integer. These are just consecutive even multiples of pi.